In this problem, an external force F is applied on a block resting on an inclined plane. The coefficient of friction between the block and the plane is mu. We have to find the range of this force F under which the block will remain stationary. Our approach to solving the problem would be to apply the force F on the block of different magnitudes, starting with a small value, then increasing it to intermediate levels, and then finally to large magnitudes. And under each condition, we would analyze all the forces acting on the block and figure out the state of the block, that is, whether it is in motion or in equilibrium. And in this process of analysis, we will be able to determine the range of force F under which the block shall be in equilibrium. So the first step in solving such problem is to draw FBD of the block. Here is the FBD showing the four forces acting on the block: weight mg acting downwards, normal force N, normal to the plane, the applied force F along the plane, and this is the frictional force which is acting upwards, because we have made an assumption that the force F is extremely small and the block is moving downwards. So this in fact is the kinetic friction. The FBD also shows the two components of the weight, mg cos alpha along the normal and mg sin alpha along the plane. By the way, we have made an assumption that angle alpha is larger than F. To be precise, it is greater than tan inverse mu. So that without any application of the external force, the block will slide down due to its own weight. So when we apply a very small force, even then the block will slide down, and therefore the direction of the friction would be opposing the motion. Therefore it will be acting upwards. Now along the normal, that is along the y-axis, there is no motion, and therefore the net force on the block would be 0, and therefore N would be equal to mg cos alpha. This equality will be true irrespective of the value of F. So for the present, we'll ignore these two forces and focus our attention only on the three forces mg sin alpha, frictional force Fr, and F, because these are the three forces which are acting along the plane and are responsible for motion of the block along the plane. So now we'll shift our attention to another diagram which shows just these three forces. So here, as you notice, that the applied force F is extremely small and is acting up the plane. The frictional force Fr is also acting up the plane, and in fact this is the kinetic friction, because the block is moving down, and its value will be equal to therefore mu k times N. But in this example, mu k is same as mu, therefore it is mu times N. Mg sin alpha is acting down the plane, and as you can notice that this magnitude is much larger than the combined magnitude of forces F and Fr. So the net force would be acting downwards, and therefore the block will move down the plane. Now if we increase this force, the externally applied force, by a little bit like this, even then the combined magnitude of frictional force and F is smaller than mg sin alpha, and therefore at this level of F the block will slide down. So now if we apply a force F which is of larger magnitude, so that the combined magnitude equals that of mg sin alpha, as you can see here in the next diagram, the combined magnitude is same as that of mg sin alpha, so the net force on the block would be 0, and therefore the body would be in equilibrium. So as we kept increasing force from a small value to larger values, this is the first point at which the block has come into equilibrium. So now this frictional force is the static friction and is at its maximum level, and the block we could say is on the verge of motion or impending motion, because if we lower the external force, that is decrease the magnitude of the force little bit, the block will slide down. But at this level, which we can call as F1, at this level of F1, the magnitude Fr and F1 combined is same as mg sin alpha, and the net force on the block is 0, and therefore the block will stay in equilibrium. So now for this condition we can write equilibrium equation like this. For normal direction we know n is equal to mg cos alpha, and for x direction F1 plus Fr minus mg sin alpha will be equal to 0. Fr is the static friction at its maximum value, and therefore will be equal to mu n, and therefore we can say F1 is equal to mg sin alpha minus mu n, and n can be now replaced with mg cos alpha, and therefore we get an expression for F1 which is equal to mg within bracket sin alpha minus mu cos alpha. So this is the lower end of the range of the force F at which the block will stay in equilibrium. We now further increase the force F more than F1. It could be like this. So now our F is this large from here to here. So combined with the frictional force, it will be now greater than mg sin alpha. So would it be correct to say that net force is acting up the plane? No, that would be wrong, because the static friction is a smart fellow and it knows that by decreasing its magnitude it can keep the body in equilibrium. So what will happen is the magnitude of frictional force will reduce to accommodate the increase in the force F, and the combined force would still be equal to mg sin alpha, as you can see from the next diagram. So here you see that the static friction has got reduced in magnitude so as to accommodate the larger magnitude of the external force, and in combination it is still equal to mg sin alpha, and therefore the net force on the block is 0 and the block is still at rest. So mind you, this force is greater than F1, but still the block is at rest. The frictional force has now reduced from its maximum level. Now if we increase F further, a situation may come that the frictional force may come down to 0 level, as you can see in this next diagram. Here the applied force has grown to an extent that its magnitude is now equal to mg sin alpha, and the frictional force has been reduced to 0. Now suppose the applied force further increases. Suppose this grows further, it may give a false impression that the net force is acting upwards, because now it is greater than mg sin alpha. Is that correct? No, it is not, because now the frictional force will flip its direction, so that now it gets added to mg sin alpha, as you can see from the next diagram. So we move from this diagram to this diagram, where the force F has increased little more. But now the static frictional force has flipped its direction. Now it is acting downwards. So in the FBD you can make out, in the earlier FBD the frictional force was acting upwards. Now it is acting downwards to provide equilibrium to the block. And this, the frictional force does it automatically on its own. It changes its direction and now gets added to mg sin alpha, so that now it becomes equal to the magnitude of the applied force, which is larger than the earlier case here. So the block is still at rest. The static frictional force has not yet attained its maximum value. It has only changed its direction. And now if we further increase the applied force to this level, the static frictional force in downward direction would attain its maximum value, and therefore now this magnitude of Fr is equal to mu n. This also is a position of rest, but now the tendency is to move up. Any slight increase in F will cause the block to begin moving up. So for this position we can again write the equilibrium equation, and this value of force we can call as F2. So F2 would be equal to mg sin alpha plus frictional force Fr, which is the equilibrium equation in x direction. F2 is equal to mg sin alpha plus mu n. We replace n with mg cos alpha and we get F2 is equal to mg within bracket sin alpha plus mu cos alpha. So in this range F1 and F2, F can keep the block in equilibrium. If the force is less than F1, the block will move down. If the force F is larger than F2, it will move up. Therefore, we can say that the range of F for equilibrium of block is this expression. F should be equal to or larger than, this is expression for F1, and F should be smaller than or equal to F2, and we have this expression for F2. And that's our answer. Thanks for watching and see you in part 2 of this video.